Here we have the harmonic series, which is the sum of the reciprocals of the natural numbers. This sum is famously counterintuitive, because even though each term is getting closer to zero, the overall sum diverges to infinity. We can see this by looking at the graph of 1 over x. Each of these rectangles has an area equal to a term in our series, starting at 1, then a half, then a third, and so on. The area of the infinitely many rectangles has the same value as the harmonic series, and visually it is easy to see that the area of the rectangles is larger than the area under the curve 1 over x. Thus, integrating 1 over x will give us a lower bound for the sum of the harmonic series. The integral of 1 over x is the natural log of x, and evaluating from 1 to infinity shows that the integral diverges. Since the integral is a lower bound, the harmonic series must diverge as well. This is known as the integral test, and works as long as the function is positive, continuous, and decreasing. If instead we alternate the sign of the terms in the harmonic series, we get the alternating harmonic series. Plotting the first many partial sums shows that the sum stays relatively bounded, oscillating around some unknown value, meaning it doesn't diverge. Computing the first 20 terms shows that this value is approximately 0.698. To prove its convergence, we can use the alternating series test. This states that as long as three simple conditions are met, any alternating series will converge. The first is that every term, ignoring the negative 1 to the n plus 1, is positive, which is true for 1 over n. Next, the terms must be decreasing, which is true because 1 over n plus 1 will always be less than 1 over n. Finally, the limit as n approaches infinity has to be 0, which is true for 1 over n. A series like this, which diverges normally, yet converges when it is alternating, is called conditionally convergent. The question now becomes, what does this alternating series converge to? A powerful technique in computing these sums is representing it as an infinite polynomial like so, where f of 1 is equivalent to our original series. Looking at each term in the original function, we can see that they look like the integrals of the powers of x. Thus, f prime is just 1 minus x plus x squared, and so on. And you may have noticed that this is the Maclaurin series for the function 1 over 1 plus x. Remember, we're looking for f of 1, so we can integrate from 0 to 1 to get from f prime back to f. Integrating from 0 to 1 gives the natural log of 1 plus x evaluated from 0 to 1, which is simply the natural log of 2.